Look up tonight, and you are not seeing the universe as it is. You are seeing a memory. The brightest star in Orion left its light behind roughly 600 years ago before it ever reached your eyes, and in that time, almost anything could have happened to the star itself. For years, scientists feared it might already be gone. New evidence says otherwise, but here is the part that will not leave you alone afterward. No one, anywhere, can ever be completely certain. Tonight, you are about to learn exactly why. There is something quietly comforting about an audience that shows up just to sit with the universe for a while. So if this kind of slow, careful unraveling is something you would want more of, liking and subscribing genuinely helps more than you would think. Not because the numbers matter to us, but because it means we get to keep doing this together a little longer. Relax your eyes and get yourself comfortable. In 3, 2, 1, liftoff. You are looking at the past right now, and there is nothing you can do about it. Every photon striking your eye from a star tonight left that star before this sentence began, before you sat down to listen, in most cases before anyone alive today was born. This is not a metaphor. This is not a poetic flourish meant to dress up an astronomy lesson. This is the literal, physical, unavoidable mechanics of light moving through space. And once you understand it fully, you will never look at the night sky the same way again. Light is fast, but it is not infinite. It travels at approximately 186,000 miles per second, a number so large that in daily life it feels indistinguishable from instantaneous. Flip a light switch, and the room brightens before you can register any delay. Point a laser at a wall across your living room, and the dot appears the moment you press the button. At human scales, the speed of light might as well be infinite, because nothing we ever interact with sits far enough away for the delay to register in any way our senses could detect. But space is not a living room. Space is so staggeringly large that even something moving at 186,000 miles every single second needs real, measurable, sometimes deeply unsettling amounts of time to cross it. And that delay, multiplied across the distances involved in astronomy, becomes the foundation for one of the strangest truths in all of science. When you look up, you are not looking at the universe as it exists right now. You are looking at a layered, fragmented record of the past, stitched together by coincidence into something that merely resembles a single moment. Let's start close to home, because the scale of this problem only becomes properly clear once you build it up piece by piece. The same way you might learn to read a map by first understanding the distance across your own street before attempting to comprehend the distance across an ocean. The Sun sits approximately 93 million miles from Earth, on average, a distance astronomers call 1 astronomical unit, a convenient shorthand that becomes useful once distances start growing too large for miles to feel meaningful. At 186,000 miles per second, light covers that 93 million mile gap in about 8 minutes and 20 seconds. That means the sunlight warming your skin on a clear afternoon left the sun's surface 8 minutes and 20 seconds before it reached you. If the sun somehow ceased to exist, this very instant vanished entirely through some impossible mechanism no known physics actually permits, you would have no way of knowing for that entire stretch of time. The sky would not go dark. The warmth would not vanish. Everything would continue exactly as it had been for another 8 minutes and 20 seconds, because the light already on its way does not carry any kind of update mechanism. Once a photon leaves a star, it is independent, severed completely from whatever happens to its source afterward. It carries no signal home. It does not check back in. It simply travels in a straight line until something stops it, whether that something is your retina, a camera sensor, or a grain of interstellar dust. And whatever happens to the object that emitted it after it departs is, to that single photon, entirely irrelevant. This 8-minute delay sounds almost trivial when you first hear it, a fun fact you might mention at a dinner party and then move on from. But it is the seed of everything that follows, because it establishes a principle that scales upward without any natural limit. The moon is so close that its light, technically reflected sunlight rather than its own emission, takes only about 1 1/4 seconds to reach Earth, a delay so brief that no human observer has ever consciously registered it without specialized equipment. Mars, depending on where it sits in its elliptical orbit relative to ours at any given moment, ranges from roughly 3 minutes, when the two planets are closest, to over 22 minutes, when they sit on opposite sides of the Sun. Jupiter, sprawling and immense in our night sky despite its enormous distance, still sits close enough that its light reaches us in somewhere between 35 and 52 minutes, depending on orbital position. Saturn stretches that delay out to somewhere between roughly 70 minutes and 90 minutes. These are delays measured in minutes, numbers that feel almost manageable, almost human in scale, the kind of gap you could fill with a short conversation or a brief walk around the block. But step outside the solar system entirely, past the outermost planets, past the icy debris of the Kuiper Belt, past even the Sun's own outermost gravitational influence, and the numbers begin to detach from anything resembling ordinary human experience. The nearest star system to our own, Alpha Centauri, sits approximately 4 3/10 light-years away. A light year is not, despite the name, any kind of measure of time. It is a measure of distance, specifically the distance light travels in exactly 1 full year, which works out to roughly 5 8/10 trillion miles, a number so large it stops being intuitively graspable and instead simply becomes a unit you accept and work with, the way you accept the existence of a mile without personally walking one every time you use the word. So when astronomers say Alpha Centauri sits 4 3/10 light-years distant, they mean its light has been traveling for 4 years and roughly 4 additional months by the time it completes its journey to your eye. Look at that star tonight, and you are seeing what it looked like during a moment that already happened years ago, a moment that is, by the time you observe it, firmly and permanently part of the past. Whatever has changed about that star since then, any flares erupting across its surface, any subtle shifts in brightness, any catastrophic event of any kind, none of it has arrived yet. You are watching a rerun of something that finished broadcasting years before you tuned in, and the live broadcast, if such a thing could even meaningfully be said to exist from your vantage point on Earth, is happening somewhere you have no access to whatsoever. Now, stretch this principle across the entire visible night sky, because here is where the truly strange part begins to take shape. Every star you can see with the naked eye sits at a wildly different distance from Earth, and because light always travels at the same fixed speed regardless of distance, every one of those different distances corresponds to a different slice of cosmic history arriving at your eye. Sirius, the brightest star in the night sky and a fixture of winter stargazing across much of the world, lies about 8 6/10 light-years away, meaning its light left less than a decade ago. Vega, one of the brightest stars visible from the northern hemisphere during summer evenings, sits at roughly 25 light-years, meaning its light departed during a period most adults alive today were already old enough to remember clearly. Polaris, the star millions of people have relied on for navigation for thousands of years, sits at approximately 431 light-years away, meaning the light reaching your eye tonight left that star before the 18th century had even concluded, before the United States existed as a nation, before most of what people now consider the foundations of the modern world had been built. Deneb, one of the most distant naked-eye stars visible in our sky, sits at a distance still actively debated among astronomers, with published estimates ranging from roughly 1,400 light-years on the conservative end to upward of 2,500 light-years on the more generous end. Take even the more conservative figure, and the light from Deneb arriving tonight left that star before the fall of the Western Roman Empire. Take the more generous figure, and that light departed before many of the earliest stone monuments in human history had been constructed. This means that when you look up at a clear night sky and take in the full sweep of visible stars stretched across the darkness, you are not looking at one universe frozen in one single instant. You are looking at dozens of entirely different moments in cosmic history, all arriving at your eyes simultaneously by pure coincidence of travel time, layered on top of each other, like transparent sheets stacked one over another, each sheet showing a different era, none of them synchronized with any of the others. Sirius is showing you something close to a contemporary view, off by less than a decade, practically current by cosmic standards. Polaris is showing you something from before electricity existed in any usable form, before the telephone, before most of what we now consider the bedrock of modern civilization had been invented. Deneb may be showing you something from before written language had spread to most parts of the world. None of these stars coordinated their timing. None of them know anything about each other's existence, let alone their respective travel times. It is simply an accident of geometry, an unplanned, unintentional convergence that their photons, departing at wildly different points across centuries or millennia of history, happen to complete their individual journeys to your specific location on Earth during the exact same evening you happen to be standing outside, looking up. Astronomers have developed precise, carefully tested ways of measuring these distances, and it matters that we walk through how, because the methods carry their own honest, openly stated uncertainty, and that uncertainty becomes critically important later, when we turn to one specific, famous star, whose distance and behavior have been the subject of intense scientific scrutiny. For relatively nearby stars, astronomers use a technique called parallax, a method whose underlying logic you can demonstrate to yourself in about 10 seconds without any equipment at all. Hold your finger up at arm's length and close one eye, then switch to the other eye. Your finger appears to shift slightly against whatever background lies behind it. That shift happens because your two eyes are observing your finger from two slightly different positions, separated by the width of your face. Astronomers exploit this exact same principle, but instead of using two eyes separated by a few inches, they use Earth's own orbit around the Sun as their separation baseline, a baseline roughly 186 million miles wide when measured from one side of Earth's orbit to the other. They observe a target star's position carefully against the background of much more distant stars that effectively do not move at all over human timescales, wait approximately 6 months for Earth to travel to the opposite side of its orbit, then Observe the same target star again from this new vantage point. The star will have shifted slightly against that distant, effectively fixed background, an apparent movement called parallax shift. And because astronomers know the diameter of Earth's orbit with extraordinary precision, refined over centuries of careful measurement, they can use simple geometric triangulation, conceptually no different from the kind of triangulation a land surveyor might use to calculate the distance to a mountain peak from two separate observation points to determine exactly how far away that star truly sits. This method works beautifully and with impressive precision for stars within a few thousand light-years of Earth, and missions like the European Space Agency's Gaia spacecraft, launched specifically for this purpose, have used it to measure the positions and distances of well over 1 billion individual stars with extraordinary accuracy, building what amounts to the most detailed three-dimensional map of our galactic neighborhood ever assembled. But parallax has hard physical limits. The farther away a star sits, the smaller its apparent shift becomes, shrinking toward angles so minuscule that even our most sensitive instruments eventually struggle to detect them reliably against the inevitable noise of measurement error. For stars beyond that threshold, astronomers turn to an entirely different technique, one based not on geometric shift, but on a star's color, its surface temperature, and its true intrinsic brightness, compared carefully against how bright it merely appears to be as seen from Earth. By studying a star's spectrum, the specific pattern of colors and dark absorption lines embedded in its light, astronomers can determine precisely what kind of star they are looking at, and, from established physical models, how bright that type of star should genuinely be if you were standing right next to it. Then, by comparing that calculated true brightness to how dim the star actually appears from our distant vantage point on Earth, they can calculate distance using the same basic logic you might use to estimate how far away a candle is, based on how much dimmer it appears compared to holding it directly in your hand. This is the method behind so-called standard candles, certain types of stars and certain types of stellar explosions whose true brightness is understood with enough confidence that astronomers can extrapolate distance reliably, even across distances where parallax becomes completely useless. Both of these methods represent remarkable achievements of human ingenuity and patient observation, and both carry honest, openly stated uncertainty ranges rather than false claims of perfect precision. A star's distance is rarely given as a single, flawlessly exact number. Instead, astronomers typically report a range, an estimate accompanied by error bars, because every measurement technique carries some inherent degree of imprecision, whether from atmospheric interference, distorting incoming light, instrument limitations at the edge of current technology, or the sheer inherent difficulty of measuring something so impossibly far away through angular shifts so impossibly small. This honesty about uncertainty is not a weakness in the underlying science. It is one of its greatest strengths, because it means that when a number is eventually reported with genuine confidence, that confidence has been earned through careful, repeated, independently cross-checked observation rather than simply asserted. So, here is where we land, with the full picture now properly assembled. Light moves astonishingly fast, but it is not infinitely fast. Distance in space is so enormous that even light's blistering speed requires years, centuries, sometimes entire millennia to cross it fully. Every star in the night sky sits at a different distance from every other star, meaning every star's light represents a genuinely different slice of the past. And these slices arrive together at your eye, not because they are synchronized in any meaningful sense, but purely because of where you happen to be standing and which specific night you happen to be looking up. The night sky, in other words, is not a snapshot. It is a collage assembled from disconnected fragments of time that have absolutely nothing to do with each other, layered together into something that merely resembles, through pure visual coincidence, a single, coherent moment. And this raises an obvious, deeply uncomfortable question, one that has occurred to nearly everyone who has ever spent enough quiet time thinking carefully about starlight. If you are seeing a star as it appeared years, centuries, or millennia ago, what is happening to that star right now, in the actual present moment you yourself are standing in? You have no way of knowing, none whatsoever. Not through any telescope currently in existence, not through any clever technique, not through any conceivable future advancement in instrumentation, because the information about that star's current state simply has not arrived yet, and it cannot arrive any faster than the fixed speed of light permits, regardless of how badly we might wish otherwise. This is not a limitation of current technology that some future scientific breakthrough might eventually solve. It is a fundamental, permanent feature of how information itself travels through the physical universe. There is no shortcut waiting to be discovered. There is no faster channel hiding somewhere in unexplored physics. Whatever is true of a given star right now will remain genuinely unknown to anyone on Earth until its light, traveling at the same fixed and unchangeable speed it always has, finally completes its journey across the gulf separating that star from us. For most of the stars scattered across the sky, this gap between past and present, while real and worth understanding deeply, does not carry much practical weight, because most visible stars remain stable across spans of time vastly longer than even the most extreme light travel delays involved. The Sun itself has burned with remarkable steadiness for roughly 4 6/10 billion years, and will continue burning in roughly its current state for billions of years still to come. An 8-minute delay in observing a star that changes meaningfully only across timescales measured in billions of years is, for all practical purposes, entirely irrelevant to anything resembling genuine uncertainty. Most stars visible in the night sky behave this way, stable, long-lived, changing so gradually and so predictably that even centuries of accumulated light travel delay reveal almost nothing meaningfully different from what remains true right now, in this present moment. But not every star plays by these comfortable, patient rules. Some stars live short, violent, dramatically accelerated lives, burning through their available nuclear fuel at a furious pace that makes the patient, billion-year stability of our own modest sun look almost leisurely by comparison, almost lazy in its restraint. These are the truly massive stars, the giants and supergiants, stars so enormous and so intensely hot at their cores that they consume their fuel reserves in a mere fraction of the time an ordinary, sun-like star requires, racing inexorably toward a dramatic, violent, and ultimately unavoidable conclusion measured not in patient billions of years, but in comparatively rapid millions. And it is precisely these stars, the short-lived giants living life on a drastically compressed timeline, where the gap between past and present stops being a quiet intellectual curiosity worth pondering over coffee, and instead starts becoming something genuinely unsettling to confront directly. Because if a star's entire remaining lifespan happens to be shorter than the time its own light takes to reach Earth, then there exists a real, physically grounded, mathematically calculable possibility that the star you are looking at directly, with your own eyes, has already completed its life cycle, already reached its violent and explosive end, and you are simply watching the final chapter of light it sent outward before that ending occurred. Light still in transit across the centuries, still arriving patiently and methodically, still glowing steadily in your sky, as though absolutely nothing has changed. There is one star, in particular, that has become, more than any other star in the entire night sky, the central focal point for this exact unsettling question. It sits within one of the most instantly recognizable constellations visible from the northern hemisphere, glowing with an unmistakable reddish-orange hue that distinguishes it immediately from the cooler blue-white stars clustered around it. For years, both professional astronomers and ordinary amateur stargazers alike have wondered, at times quite anxiously, whether this particular star might have already met its violent end, its final burst of light, still patiently making its way across the centuries to eventually reach us here on Earth. And, recently, the established science surrounding this exact star has shifted in a way that demands careful, thorough, and honest explanation, because the real story turns out to be more genuinely interesting, more scientifically nuanced, and ultimately more reassuring than the simplified popular version most people have casually heard repeated. That star is Betelgeuse. And to understand why it became the single most famous example of the already dead question in all of popular astronomy, you have to understand exactly what kind of star it is, exactly how far away it sits, and exactly what has happened to the science surrounding it over the past several years, because the story of Betelgeuse is not simply a quiet tale about an old, dying star sitting patiently in the sky, waiting out its inevitable end. It is a genuine scientific mystery, a story about documented uncertainty, about a real puzzle that worried serious professional astronomers for years, and about a discovery so recent and so significant that it fundamentally rewrote the timeline almost everyone, including many experts, had come to believe was settled. Betelgeuse sits in the constellation Orion, marking the hunter's right shoulder, easily visible from the northern hemisphere's sky during the winter months as a distinctly reddish point of light, standing out sharply against its neighboring blue-white stars. That reddish color is not a coincidence or some artistic flourish added for visual interest. It is direct, observable visual evidence of the star's actual surface temperature, which sits at approximately 6,300 degrees Fahrenheit, dramatically and meaningfully cooler than our own sun's surface temperature of roughly 10,000 degrees Fahrenheit. In stellar physics, cooler surface temperatures correspond reliably to redder colors, while hotter surfaces glow blue and white, the exact same basic physics that makes a heating element glow a dull, sullen red at lower temperatures and a brilliant, almost painful white-blue at much higher ones. Betelgeuse's relatively cool surface, combined with its truly staggering physical size, places it firmly within a category of stars known as red supergiants, among the largest individual objects astronomers have ever been able to directly study and characterize. And the size truly is almost impossible to comprehend properly, even with careful effort. Betelgeuse's radius is currently estimated at somewhere between 700 and 900 times the radius of our own Sun, meaning that if you replaced our Sun with Betelgeuse while leaving every planet exactly where it currently orbits, the star's outer surface would swallow Mercury, Venus, Earth, and Mars entirely without resistance, extending outward to somewhere in the general vicinity of Jupiter's own orbital path. More than 400 million suns could fit comfortably within the total volume Betelgeuse occupies. This is not a star you could meaningfully compare to anything found in ordinary human experience, because nothing in ordinary human experience operates anywhere near this scale. It exists in a category of cosmic objects that simply overwhelms every intuition we have ever built through the course of everyday life on a small rocky planet. Betelgeuse's mass tells a related but genuinely distinct part of this story. Current scientific estimates place its mass at somewhere between 16 and 19 times the mass of our own Sun. And this particular number matters enormously because, in stellar physics, mass functions essentially as destiny. The more massive a star happens to be, the more intense the gravitational pressure crushing inward on its core, the faster it burns through its available nuclear fuel, and the more violent and rapid its eventual death becomes. Our own Sun, carrying a single solar mass, will continue burning steadily for billions of years still to come, before gently expanding into an ordinary red giant, and eventually settling quietly into a cooling white dwarf, fading slowly across unimaginable spans of time, with no explosive finale required whatsoever. Betelgeuse, carrying somewhere between 16 and 19 times that mass, faces an entirely different and far more dramatic fate, one defined fundamentally by speed and eventual violence rather than slow, graceful decline. Massive stars of this general type are estimated to have total lifespans measured only in the millions of years rather than billions, and Betelgeuse itself is currently estimated to be roughly 8.5 million years old, already deep into what astronomers widely consider the final phases of stellar evolution available to an object carrying this much mass. Now consider the distance involved, because this is where the story begins to take on its full unsettling weight. Betelgeuse sits somewhere between approximately 548 and 640 light-years from Earth, with different measurement techniques and different independent research teams arriving at slightly different figures within that overall range, a figure commonly rounded in popular discussion to approximately 650 light-years, purely for simplicity and ease of conversation. Take the more commonly cited figure, and you arrive at a genuinely striking realization. The light from Betelgeuse currently reaching your eyes left that star's surface approximately 650 years ago, sometime around the period of significant upheaval unfolding across 14th and 15th century human history, well before the printing press had spread widely across Europe, centuries before anyone alive today, anyone's grandparents, anyone's great-great-grandparents, removed by many generations, had been born into the world at all. Whatever Betelgeuse happens to be doing right now, in this exact present moment as you read these words, will not become visible from Earth until sometime around the 27th century, an almost incomprehensible span of patience required simply to receive a single update on its current status. Here is where the genuinely fascinating part of this particular story properly begins, because Betelgeuse did not earn its widespread reputation as the star that might already be dead purely through abstract reasoning about distance and stellar mass alone. It earned that reputation through real, carefully observed, precisely measured behavior that genuinely puzzled professional astronomers for a period of years and generated legitimate, well-documented scientific concern. not merely idle public speculation circulating online. In late 2019 and continuing into early 2020, Betelgeuse began dimming dramatically, an event astronomers later came to nickname the Great Dimming. Betelgeuse has always varied somewhat in brightness across time, a perfectly normal characteristic for stars of its particular type and evolutionary stage. But this specific dimming event was meaningfully different in both scale and duration from anything previously documented in the star's observational history. The star's overall brightness dropped to roughly 40% of its typical level, a change so dramatic that it became noticeable even to careful naked eye observers without any specialized equipment whatsoever. Simply by looking upward on a clear winter night and noticing that one of the sky's most reliably bright and familiar stars had grown noticeably, unmistakably dimmer than usual. For professional astronomers who had spent years monitoring stellar behavior closely across the sky, and for dedicated amateur stargazers who had spent comparable years becoming intimately familiar with Betelgeuse's typical seasonal appearance, this sudden change was genuinely startling. Stars of this size and stability do not typically dim by such a significant margin without something meaningful happening somewhere within or around them. The timing of this event made the resulting concern feel especially urgent because Betelgeuse had already been a subject of recurring supernova speculation for years prior to the Great Dimming itself. As early as 2009, careful observations had suggested the star's apparent angular size might have contracted by as much as 15% over the preceding years, fueling early rumors and speculative discussion, suggesting the star might already be entering some kind of internal collapse phase. Those earlier rumors had never been definitively confirmed or thoroughly ruled out by subsequent research, simply lingering quietly in the background of public astronomical interest for roughly a decade. When the Great Dimming finally arrived in earnest, that long-lingering uncertainty erupted almost overnight into widespread, genuinely serious speculation across both scientific circles and popular media. News outlets around the world ran prominent headlines openly asking whether humanity might be on the verge of witnessing the first naked-eye supernova visible from our own galaxy in several centuries. Astronomers fielded an absolutely enormous wave of public interest alongside genuine, well-founded scientific curiosity from their own colleagues. Telescopes positioned around the entire globe turned their collective attention toward Orion's shoulder, watching closely, night after night, for any further sign that this unprecedented dimming might represent the prelude to the star's final, explosive ending. The dimming eventually reversed on its own. By early 2021, Betelgeuse's overall brightness had returned to something closely resembling its typical historical range, and the star had clearly not exploded after all. But the precise explanation for what had actually caused the dimming in the first place took considerably longer to fully resolve through careful follow-up research, and in the meantime, broader scientific uncertainty about the star's underlying long-term stability persisted stubbornly. Researchers eventually determined, through careful spectroscopic analysis and follow-up observation, that the Great Dimming had most likely been caused by a massive ejection of stellar material erupting outward from the star's southern hemisphere, material that subsequently cooled rapidly enough after being violently expelled to condense into a dense, opaque cloud of fine dust particles, a cloud that then drifted directly between Betelgeuse and Earth's specific line of sight, temporarily blocking a significant and measurable portion of the star's light from ever reaching us during that window of time. This explanation made reasonable physical sense and fit tolerably well with established scientific understanding of how red supergiants generally behave as they continue aging, periodically shedding outer material through ongoing stellar winds and episodes of intense surface activity. But this explanation raised its own important follow-up question that lingered unresolved for years afterward. Was this kind of dramatic, large-scale mass ejection itself a meaningful warning sign of a star rapidly approaching the final, genuinely unstable phases immediately preceding core collapse? Or was it simply normal, if visually dramatic, behavior for an aging red supergiant that still had a substantial amount of stable time remaining ahead of it? This particular question grew measurably more urgent rather than less. So, as researchers continued carefully studying Betelgeuse's ongoing behavior in the years immediately following the Great Dimming event, beyond the dust-related dimming episode itself, astronomers had already long known that Betelgeuse's overall brightness varies according to two separate, overlapping cyclical patterns layered on top of each other. One of these cycles, lasting approximately 400 days from peak to peak, was reasonably well understood by researchers and confidently attributed to ordinary pulsations occurring within the star itself, a kind of rhythmic expansion and contraction common among stars at this particular evolutionary stage, somewhat resembling a slow, massive breathing pattern stretched out across more than a full calendar year. But a second, considerably longer cycle, lasting approximately 2,100 days, or roughly 5 7/10 years, from peak to peak, had no clear, widely agreed upon explanation whatsoever among the research community. This longer secondary cycle had been carefully observed and tracked across many years of accumulated data, but the underlying physical mechanism actually driving it remained genuinely mysterious, a real and substantively unresolved scientific puzzle, rather than some merely settled detail, simply waiting to be neatly summarized in a textbook. In 2023, this lingering scientific uncertainty took a considerably sharper and more alarming turn. A research paper published that year focused specifically on analyzing Betelgeuse's various pulsation periods in careful mathematical detail, suggested an evolutionary stage for the star that appeared consistent with a supernova occurring not in some comfortably distant future, measured in tens of thousands or even hundreds of thousands of years, but potentially within a time frame of mere tens of years. An almost shockingly compressed and immediate timeline by ordinary astronomical standards. This particular paper drew significant and sustained attention within the broader astronomical research community and contributed meaningfully to a growing sense among both experts and the interested public that Betelgeuse might genuinely be approaching the true end of its life far sooner than previously assumed by most researchers, that the still unexplained 5 7/10 year brightness cycle and the dramatic Great Dimming event might both represent early, if cryptic, warning signs of an imminent and dramatic ending, the exact kind of ending that, if it had somehow already occurred, would necessarily mean Betelgeuse's actual deathlight was already in active transit, working its way steadily across more than 6 full centuries of empty interstellar space toward an Earth that currently had absolutely no idea anything catastrophic had occurred at all. This is the precise point in Betelgeuse's unfolding story where the already dead question stopped functioning as purely theoretical speculation and instead became, for several genuine years running, a live and pressing scientific and public concern simultaneously. Astronomers were not simply indulging in idle, baseless speculation when they seriously wondered whether Betelgeuse might already have exploded somewhere in the recent past. They were responding directly to real, carefully documented, thoroughly peer-reviewed behavior, an unprecedented and dramatic dimming event, a long-standing mysterious brightness cycle, still lacking any settled explanation, and a published, peer-reviewed research paper explicitly suggesting a supernova timeline measured in mere decades rather than comfortable millennia. Combine all of this accumulated uncertainty with the star's roughly 650 light-year distance from Earth, and you arrive at a scenario that is not merely poetic or unsettling purely in the abstract, but one grounded firmly in specific, documented, peer-reviewed, scientific concern shared by working astronomers. If Betelgeuse's true remaining lifespan genuinely was measured in mere decades, as that 2023 paper had suggested was plausible, and its light simultaneously takes over 6 full centuries to reach Earth from where it sits, then there existed a real, mathematically calculable possibility that the star had already exploded at some point in the relatively recent past, conceivably even within living memory of people alive today, with the light revealing this catastrophic event to Earth's eventual observers, simply still en route across the intervening centuries, with absolutely no way for anyone here to know for certain until that light finally, eventually arrived. For several years following that 2023 paper, this uncertainty simply persisted, stubbornly unresolved, a genuine open question hovering directly over one of the night sky's most recognizable, most beloved, and most carefully watched individual stars. Astronomers continued monitoring Betelgeuse closely throughout this period, tracking its brightness fluctuations night after night, studying its full spectrum in painstaking detail, watching attentively for any further unusual behavior that might offer additional useful clues toward finally resolving the underlying mystery. The mysterious 5 7/10 year cycle remained stubbornly unexplained. The precise mechanics of the Great Dimming remained only partially understood at best, and the very real possibility that Betelgeuse might already be gone, its final light steadily counting down toward an arrival date no researcher could meaningfully predict in advance, remained genuinely open, neither convincingly confirmed nor definitively ruled out, sitting persistently in that deeply uncomfortable space between established scientific fact and lingering, entirely legitimate scientific uncertainty that no one had yet managed to fully close. But uncertainty in science is rarely a permanent or final state, and Betelgeuse's unfolding story was about to take a genuinely significant turn, one that would resolve much of this lingering mystery in a way that very few people, even careful, long-time professional observers of this particular star, had fully anticipated arriving when it finally did. The answer, when it eventually arrived, would not come from simply watching Betelgeuse itself more closely than before, but from discovering something else entirely, something hidden quietly in plain sight all along, something that had apparently been shaping Betelgeuse's strange behavior the entire time without a single researcher realizing it was actually there. The answer arrived not through a single dramatic announcement, but through nearly 8 years of patient, accumulating observation, the kind of slow scientific detective work that rarely makes headlines until the final piece locks into place. Researchers at the Center for Astrophysics, a joint research institution operated by Harvard University and the Smithsonian Institution, had spent those years quietly monitoring subtle changes in Betelgeuse's light, using NASA's Hubble Space Telescope alongside several ground-based observatories, including the Fred Lawrence Whipple Observatory and the Roque de los Muchachos Observatory. They were not looking for a supernova warning sign specifically. They were looking for something more fundamental, a consistent, repeatable pattern hidden within the noise of Betelgeuse's spectrum that might finally explain the mysterious 2,100-day cycle that had puzzled astronomers for so long. What they found, confirmed and announced in July of 2025, was a companion star, a previously undetected, much smaller star, later given the name Siwaha, orbiting Betelgeuse at an extraordinarily close distance, roughly 4 astronomical units, a distance comparable to the gap between our own Sun and the planet Jupiter. The idea that Betelgeuse might have a hidden companion had circulated among astronomers as a working hypothesis for years prior to this confirmation, a plausible explanation that kept surfacing in theoretical discussions without ever being directly proven through observation. Without solid, direct evidence, it remained an unconfirmed theory, one possibility among several competing explanations for the star's strange long-term behavior. The 2025 discovery changed that entirely, providing the first genuinely direct evidence that something real and physical was orbiting Betelgeuse all along, hidden from view simply because Betelgeuse itself is so overwhelmingly large and so overwhelmingly bright that a comparatively small, faint companion star sitting in such close proximity had effectively been drowned out, lost in the glare of its enormous neighbor for as long as anyone had been watching. Confirming the companion's existence was only the first step, however. The far more interesting question, the one that would ultimately resolve the entire Great Dimming Mystery and the unexplained brightness cycle alongside it, was what this companion star was actually doing as it completed each orbit. And the answer to that question came from a follow-up study presented at the 247th meeting of the American Astronomical Society in Phoenix and accepted for publication in the Astrophysical Journal in January of 2026, led by astronomer Andrea Dupree of the Center for Astrophysics. Here is the mechanism, and it is worth understanding properly because it resolves nearly every piece of the puzzle that had accumulated over the preceding years. Betelgeuse is so enormous, with a radius somewhere between 700 and 900 times that of our own Sun, that its outer atmosphere extends vastly beyond what most people would intuitively think of as the star's true surface, a diffuse, extended envelope of gas, stretching outward for a substantial distance before finally thinning into the surrounding vacuum of space. Siwaha's orbit, at roughly 4 astronomical units, brings it close enough to Betelgeuse that the smaller star does not simply circle gracefully outside this envelope. It actually plunges directly through Betelgeuse's extended outer atmosphere during each pass, moving through that thin, diffuse gas the same way. A boat moving through water disturbs the surface and leaves a visible wake trailing behind it. As Siwaha moves through this gas, it physically stirs and compresses the material immediately behind it, creating a dense, swirling wake of disturbed gas that trails the smaller star throughout its orbit. This wake is not subtle. Researchers tracking the precise wavelength shifts in light coming from Betelgeuse's atmosphere, specifically ultraviolet light emitted by ionized iron, found a clear and consistent pattern when Siwaha sat positioned in front of Betelgeuse from Earth's vantage point. The light showed a noticeably stronger blue shift, meaning material was moving rapidly toward Earth's direction. When Siwaha sat behind Betelgeuse instead, that same blue shift weakened considerably. This pattern repeated reliably, tracking precisely with Siwaha's orbital position, and it matched almost exactly what theoretical models had predicted a companion star's wake should look like if one truly existed. The supergiant's own atmosphere, already flowing outward under normal stellar wind processes, was absorbing and carrying this wake forward after Siwaha passed through, exactly as the boat and water analogy would suggest. This single mechanism, once properly confirmed through years of careful spectroscopic monitoring, explained the long mysterious 2,100-day brightness cycle directly and convincingly. The cycle was not some unexplained internal instability deep within Betelgeuse itself, not a warning sign of impending core collapse, not evidence the star was approaching some unstable terminal phase. It was simply the predictable, periodic signature of Siwaha's orbit, repeating itself roughly every 5 7/10 years as the smaller star completed each full circuit, plowing through the same extended atmosphere and leaving the same kind of disturbed wake behind it every single time. A genuine scientific mystery that had persisted for years, generating real concern among professional astronomers, turned out to have an answer rooted not in stellar death, but in stellar companionship. This discovery also reframed the earlier Great Dimming event itself in a more complete light. While the dimming had already been attributed to an ejected dust cloud temporarily blocking Betelgeuse's light, the existence of a close, orbital companion physically disturbing the star's extended atmosphere on a regular cycle gave researchers a far more complete picture of why Betelgeuse behaves the way it does more broadly, why its atmosphere shows the particular patterns of disturbance and outflow that it does, and why a star of this type might periodically eject material from its surface in the dramatic way the Great Dimming had demonstrated. Rather than two unrelated mysteries sitting side by side, both the long-term brightness cycle and the broader pattern of atmospheric disturbance now fit within a single, coherent physical picture centered on Siwaha's repeated passage through Betelgeuse's outer layers. The discovery did not stop with explaining past behavior. It directly addressed the most pressing question of all, the one that had driven years of public anxiety and scientific debate alike. When, realistically, will Betelgeuse actually explode? Here, the new evidence pointed firmly away from the alarming 2023 estimate of mere tens of years. The detailed spectroscopic evidence gathered through this companion star research, combined with broader modeling of Betelgeuse's current internal state, indicated that the star is currently in a stable helium-burning phase, a well-understood and comparatively long-lasting stage of stellar evolution that occurs before the more rapid, unstable burning phases that immediately precede core collapse. Based on this evidence, researchers now estimate that Betelgeuse likely has hundreds of thousands of years remaining before it actually reaches the point of supernova, a timeline that supersedes and substantially revises the far shorter estimate that had circulated since 2023. This revision matters enormously for how the entire story should be understood, and it deserves to be stated plainly rather than glossed over. The 2023 paper was a legitimate, peer-reviewed piece of research, and the concern it generated was not irrational or unfounded at the time it was published. It was a reasonable interpretation of the data available then, before the companion star and its wake had been confirmed. Science working properly looks exactly like this. An initial finding raises a serious possibility. That possibility gets tested and scrutinized through years of additional observation. and new evidence eventually either confirms or substantially revises the earlier picture. In this case, the picture was revised toward considerably more time, not less. The mysterious behavior that once looked like it might be an early warning sign of imminent core collapse turned out, once properly understood, to be the signature of an entirely different and far less alarming phenomenon. A small companion star, quietly orbiting through a giant's atmosphere, exactly as it likely has been doing for a very long time already. Siwaha itself has its own story worth briefly noting, because it adds one final layer of texture to this picture. Researchers studying the companion's orbit determined that gravitational forces are gradually drawing Siwaha closer to Betelgeuse over time, and current estimates suggest the two stars may actually merge within roughly 9,000 to 10,000 years, an outcome that would occur long before Betelgeuse itself reaches its eventual supernova. Should that merger occur, astronomers expect it would release a burst of additional gas, alter Betelgeuse's rotation, and potentially influence the eventual properties of the supernova that follows much later. From Earth's current vantage point, Siwaha sits positioned behind Betelgeuse in its orbit, meaning the companion star is not currently visible even to the powerful instruments that detected it. Researchers are already planning a new round of observations timed for Siwaha's next favorable emergence, expected in November of 2027, when the two stars will once again sit at their widest apparent separation as seen from Earth. So where does this leave the central question that opened this entire investigation? Betelgeuse's light, the light reaching Earth tonight, left that star's surface roughly 650 years ago, and there remains, as there always will, no way to directly observe what is happening at Betelgeuse in the present moment. That fundamental, irreducible fact about light travel time has not changed and cannot change. What has changed is the weight of evidence concerning what was almost certainly true throughout that 650-year journey, and what is almost certainly still true today. The star that briefly looked, in the years following 2023, like a strong candidate for having possibly already exploded now looks, based on the most current and thoroughly confirmed peer-reviewed science available, like a star settled comfortably into a long, stable phase of its life, with a companion star calmly orbiting through its outer atmosphere every 5 7/10 years, and with an estimated few 100,000 years still remaining before any supernova becomes a realistic possibility. This resolution, satisfying as it is, does not actually close the deeper question this entire story has been building toward. It only resolves it for one specific star, at one specific moment in scientific history, based on evidence gathered up through the most recent observations available. The light still takes 650 years to arrive. The present moment at Betelgeuse remains, and will always remain, fundamentally inaccessible to anyone standing on Earth. And Betelgeuse, for all its newfound clarity, is only one star among countless others scattered across the night sky, most of which have never been studied with anywhere near this level of scrutiny, most of which carry no comparable companion star discovery to settle their own uncertain timelines. To understand what any of this truly means, for Betelgeuse, for the rest of the sky, and for what it means to look upward at all, requires turning away from the specifics of one star's biography and toward the actual physical mechanics of how a star like this dies in the first place, and toward the deeper, more permanent truth about knowledge and time that no future discovery, however reassuring, will ever fully erase. To understand what it would actually mean for a star to already be dead, you have to understand what death looks like for a star massive enough to die this way. Because dead star is not a vague, poetic phrase borrowed for dramatic effect. It describes a specific, violent, thoroughly studied physical process, and walking through that process carefully is the only way to make everything explored so far, the questions about Betelgeuse, the broader questions about the rest of the sky, actually mean something concrete, rather than something merely atmospheric or unsettling in a vague, undefined way. A star like Betelgeuse spends almost the entirety of its life fusing hydrogen into helium at its core, the same fundamental nuclear process powering our own modest sun, simply happening at a far more furious, accelerated pace given the star's enormously greater mass. Hydrogen fusion is, in a sense, the easy phase, the long, stable plateau every star of sufficient mass passes through before anything dramatic begins. Once the hydrogen fuel at the core is finally exhausted, gravity, no longer held at bay by the outward pressure of ongoing fusion, compresses the core further, raising its temperature high enough to ignite a new fusion process, helium burning, converting helium into carbon and oxygen. This is the phase current research indicates Betelgeuse occupies right now, a comparatively stable, long-lasting stage that can persist for a meaningful span of time, measured in many thousands of years, for a star of this mass, before the next transition becomes necessary. As helium fuel runs low in turn, the same pattern repeats, but each repetition happens faster than the one before it, compressing further and further as the star races toward its eventual conclusion. The core contracts again, heats further still, and begins fusing progressively heavier elements in rapid succession, carbon into neon and magnesium, then neon into oxygen and magnesium, then oxygen into silicon and sulfur, then, finally, silicon into iron and nickel. Each of these stages burns through its available fuel faster than the stage preceding it, a pattern driven by simple physics, since heavier elements release proportionally less energy per fusion reaction, even as they require proportionally higher temperatures and pressures to ignite at all. Carbon burning might last several hundred years. For a star of this mass, neon burning might last only around 1 year. Oxygen burning might last a matter of months. And by the time a star this massive finally reaches silicon burning, the entire stage may last only a single day, sometimes less, before the core finishes converting itself almost entirely into iron and nickel, with essentially nothing left to fuse afterward that could release additional energy. Iron is where this entire cascading process stops, abruptly and catastrophically, because iron occupies a uniquely terminal position in nuclear physics. Every fusion reaction up to this point has released energy outward, energy that pushes back against the relentless inward pull of the star's own gravity, holding the star's enormous bulk stable against collapse for millions of years. Fusing iron does the opposite. It consumes energy rather than producing it, meaning the moment a star's core becomes dominated by iron, the outward pressure that has propped up the entire structure for the star's whole life simply vanishes, all at once, with nothing left behind to replace it. There is no slow transition here, no gradual winding down. The core, suddenly unsupported, collapses in a fraction of a second. An entire region, roughly the size of Earth, crushing down into something potentially no larger than a city in less time than it takes to read this sentence aloud. That collapse does not simply continue indefinitely. The infalling material rebounds violently off the newly formed, incredibly dense core, sending a shockwave tearing back outward through every layer of the star still positioned above it. That shockwave, combined with an almost unimaginable burst of energy released during the collapse itself, blasts the star's outer layers outward into space at speeds reaching tens of thousands of miles per second, briefly generating more energy than an entire galaxy of ordinary stars combined. This is a supernova, not a gradual fade, not a quiet conclusion reached slowly over careful decades, but one of the single most violent and sudden events the known universe is capable of producing, beginning and essentially completing within a span of mere seconds at the core, even as the visible brightening that follows can take hours or days to reach its peak as the shockwave works its way outward through the star's remaining bulk before finally breaking through the surface. There is one additional detail worth understanding here, because it adds a genuinely strange wrinkle to the entire light travel time question this investigation has been built around. The collapse itself releases an enormous burst of neutrinos, tiny, nearly massless particles that interact so weakly with ordinary matter that they pass almost effortlessly through the entire remaining bulk of the dying star, escaping into space within seconds of the core's collapse, long before the visible shockwave has even finished its journey outward through the star's outer layers. This means that, in principle, a burst of neutrinos from a nearby supernova could reach Earth's detectors hours before any visible brightening becomes apparent in the sky, a strange, narrow window in which the death of a star would already be detectable through instruments built specifically to catch these elusive particles, even while the star still appeared, to any observer simply looking upward with the naked eye, completely unchanged. Detectors built for exactly this purpose already exist and operate continuously, waiting for a burst that has not yet arrived from any sufficiently close star, a quiet, patient form of monitoring running in the background of modern astronomy. If Betelgeuse had already reached this point sometime in the past, the actual moment of core collapse would have unfolded in this same, almost instantaneous fashion, and the resulting light, along with that initial burst of neutrinos, would already be in transit, with nothing left to do but wait for it to arrive. There is no slow leak of warning signs visible from Earth in the years immediately before such an event finally reaches us. No gradual dimming we could point to with genuine certainty as proof something catastrophic is imminent, because by the time any such evidence reaches Earth, the event itself would already be roughly 650 years in the past, the explosion already finished, the star already transformed into either a neutron star or a black hole, depending on exactly how much mass it had to begin with. The mechanism described here is real, well understood through decades of careful theoretical and observational work, and genuinely possible for a star of Betelgeuse's mass. What current evidence indicates, based on the Siwaha discovery and the stable helium-burning phase it revealed, is that this mechanism has very likely not yet begun for Betelgeuse, and is not expected to begin for a few 100,000 years still to come. That is the honest, present-day answer for this specific star, earned through years of careful, patient observation rather than simply assumed out of optimism or convenience. But Betelgeuse was never the only star for which this question genuinely matters, and it would be a disservice to end this investigation here. As though one resolved case settles the broader truth, the entire story has been building toward from the very beginning. Betelgeuse happens to be close enough, bright enough, and famous enough that it received nearly 8 years of dedicated Hubble observation time and a peer-reviewed companion star discovery capable of resolving its specific uncertainty. Most stars receive nothing close to that level of scrutiny, simply because there are far too many of them and far too few telescopes, far too little observation time to study every candidate this thoroughly. Scattered across the night sky are other massive, short-lived stars sitting at distances of several thousand light-years rather than hundreds, stars whose remaining lifespans genuinely may be shorter than the time their light takes to reach us, and for which no equivalent companion star discovery has come along to settle the question one way or the other. For these stars, the original premise this entire episode opened with still stands essentially untouched. A star with a remaining lifespan of mere centuries, sitting several thousand light-years away, could have already completed its life and exploded, and the light currently reaching Earth would show no detectable difference whatsoever from the light of a star that still has considerable time left, right up until the moment the actual death light, the visible signature of core collapse itself, finally arrives without warning. History has already demonstrated this exact scenario playing out, more than once, in ways carefully documented at the time. In 1604, observers across multiple cultures and continents recorded a brilliant new point of light appearing suddenly in the sky, bright enough to remain visible during daylight hours for weeks at a stretch, an event astronomers now refer to as Kepler's supernova, named for the astronomer Johannes Kepler, who documented and studied it carefully using the instruments available to him at the time. The star that produced that explosion had already died well before that light ever arrived. The actual collapse occurred years, possibly decades, earlier, the star simply continuing to appear unremarkable and unchanged in the sky to anyone observing it, night after night, until its death light finally completed its long journey and announced, seemingly all at once, an ending that had in fact already happened far in the past. A similar event occurred in 1572, recorded with great care by the astronomer Tycho Brahe and now known as Tycho's supernova, an observation that itself helped challenge the long-standing ancient belief that the heavens were fixed and unchanging, since here was direct, undeniable proof that something in the supposedly eternal sky had visibly, dramatically changed within a single human lifetime. And sometime around the year 1680, by the best current estimates available to astronomers today, a star roughly 11,000 light-years away exploded, producing what is now known as the supernova remnant Cassiopeia A. Yet no clear historical record exists anywhere of anyone on Earth noticing a new star appear in the sky at that time, the event apparently passing almost entirely unrecorded by the observers of that era, despite its eventual light reaching Earth regardless, arriving on schedule, whether or not anyone happened to be looking, whether or not anyone wrote it down, whether or not anyone understood what they were witnessing, even if they had glanced upward at exactly the right moment. The universe does not require an audience for its events to occur, and it does not pause its own timeline waiting for someone to notice. These are not hypothetical scenarios constructed for the sake of this episode. They are documented history, verified across multiple independent records, and confirmed through modern astronomical analysis of the remnants those explosions left behind. Stars have died. Their light has taken years or centuries to arrive, and observers on Earth went about their ordinary lives entirely unaware that anything catastrophic had happened until the sky itself finally announced it, often without any warning whatsoever, on a night that had looked, the evening before, exactly like every other ordinary evening that came before it. This is the place where the entire investigation finally settles, not into anxiety and not into simple reassurance either, but into something quieter and more permanent than both. The night sky has never been a live broadcast of the present moment, and it never will be, regardless of how advanced telescopes eventually become, regardless of what future companion stars get discovered through years of patient observation, regardless of how many remaining mysteries science manages to resolve through careful, accumulating evidence. Every point of light overhead represents a separate fragment of the past, arriving together at your eye through nothing more than coincidence of distance and timing. None of it synchronized, none of it current, all of it true only in the narrow sense that it was true at the moment it departed its source. Betelgeuse, as far as the best available evidence can currently establish, is very likely still there tonight, still burning steadily through helium in its core, with an extraordinarily long road still ahead of it before anything resembling an ending arrives. But that word, likely, is doing real work in that sentence, carrying real weight, and it is the most certainty anyone will ever genuinely have about Betelgeuse, or about any star sitting far enough away that its light has been traveling longer than a single human lifetime allows. The sky above you tonight is not lying to you, and it is not hiding anything from you either. It is simply showing you exactly what it has always shown anyone who has ever looked up across the entire span of human history. Not the universe as it is in this present instant, but the universe as it was, patiently delivered, one photon at a time, across distances that make the word now lose almost all of its meaning the moment you point it at the stars. You will go back outside again on some ordinary night and look up, and you will see Orion's shoulder glowing faintly red exactly where it has always been, and you will know, in a way you did not know before, that what you are looking at is not a star existing in this moment, but a memory of one, traveling toward you across 6½ centuries, arriving precisely on schedule, indifferent to whether anyone below happens to be watching at all.